most of you have got used to these online systems nowadays. So I hope you are able to see the slides. I hope everyone is able to see the slides. If there's any problem, the organizers can interrupt me and we can adjust or do something. Yeah. Is the first slide visible? The ordinary?
Not yet, sir.
Is that so? Just some time ago it was visible. Okay. Once again, let me do, because we have shifted, is it not? So Chrome tab I should, because in between I'll change this slides also. I hope now it has come. Has it come?
Yes, sir.
Yeah, it has come.
Yes.
Yes, it has come. Yes.
Yeah. Good afternoon. Let me welcome you all to this overview or crash course sort of thing on this topic, differential equations. Okay. So as you know, this is one of the very useful subjects in mathematics and in IISc for your coursework and many things. The purpose of giving this is to make a review of some techniques that you may have already learned. Okay, I know many of you have been studying differential equations at different levels, both the college and maybe for some of you may be needing for your research also. But of course, I am looking at it from an interest point of view. One of the most important reasons why we learn something is because we are interested in that. Of course, other reason is that it is useful for you in your research or in the coursework and so on. Okay, so let us look at it that way. This is only a very short duration lecture, so we may not be able to cover everything, but I would definitely take this opportunity to tell everyone that let us look at many of the things from an interest point of view, not usefulness point of view. Usefulness will definitely come. Okay, let us get going. So I have taken this set of some material from the Kreyszig's book. I have mentioned in the notice that we'll use the Kreyszig's book. Part 1 of the book consists of these differential equations. A lot of things are there in that, many examples and so on. But I have taken a subset of that. Okay, let us get going. So as you know, these are the broad contents I wanted to put, but most likely I have put only maybe the systems I have not put much. And many other things I have put. Systems I have not touched much in this two sets of slides I have. So as you know, differential equations are the equations which contain derivatives. So the idea of derivatives itself is a very strange thing, very novel thing. And of course, now we are very familiar, but it's a very strange thing to differentiate a function once upon a time, just when it was invented during Newton's time. People were thinking, what is this derivative? And of course, for a long time in the college curriculum also, we are very perplexed by what is this derivative. See, I'm taking a view that we are trying to think what it is, not just what is represented by this notation. One of the important problems or convenience, both problem as well as convenience, is the notation. So notation will simply distract your thinking sometimes, and sometimes it will help. So you should be very cautious about. And in fact, because we are talking about I hope many of you are interested in the applications and engineering aspects of that. You always have the physical models. So you must imagine what is this mathematics representing. Okay. So a differential equation is an equation which consists of derivatives. So you know, derivatives can be of different orders. I will not go very rigorously. See, the mathematics people will kill me if I go this particular way. But if I want to really understand, first step is to get to the concepts. What is this? Why is this like this? And so on. Then, of course, comes the utility, or sometimes you may want to learn for the examinations and all that. But I think the basic way of looking at things is to understand for yourself, either from a book or a lecture from this and so on. So a differential equation is the one which contains derivatives. Like there are a lot of notations are there: y dash, y double dash, y triple dash, etc. Or derivatives of different orders. There are a lot of examples. Equations, of course, as you know, there will be right hand side and left hand side, and you equate them. And you can transpose from this side to that side to this side, and to the denominators, and so on and so forth. You can construct equations in many forms. and many ways and appearances. Some of them, of course, can be put in some standard form. Most of the time you put equations in some standard forms and then try to address them or solve them and so on and so forth. So of course there are also other, in contrast, we should contrast this differentially ordinary, the word ordinary, with what is called this partial. You know, derivatives can be ordinary derivatives or partial derivatives. If you have a function of several variables, then you can differentiate with respect to different variables, and so you have partial derivatives. So equations which contain partial derivatives will be called partial differential equations. We may not touch them in this part 1 of this chapter. Okay, and of course a lot of variations, a lot of features are there of these derivatives. We'll highlight as and when we go along. Okay, so whenever the time is up, the organizers can cut me. So as you know, why do we want to study these differential equations? So they appear in many areas of engineering and science. For example, I have given 2 examples from the book. So the falling of a stone is a very good example and is given by y double dash equals to the gravitational constant. And you can look at the motion. And of course, it's a very simplest form I have put here. So you can represent it in many ways, because as you know, the physical quantities like velocity, acceleration, etc. are all described or defined in terms of the derivatives. So definitely you can expect that the derivatives will come into these equations of motion. Similarly, in the electrical engineering, you have a lot of circuits. So this is an example of an LCR circuit, and you know that the parameters like the capacitance, inductance, etc. can be defined in terms of the derivatives of currents, voltages, and so on. So you will get a lot of differential equations in electrical circuits also. So I would like to take a slightly more modern view. See, in olden days, there were not much computational power. So people used to solve them by hand, and so a lot of techniques have been derived. A lot of techniques to address these, to interpret these, to solve these are available. But nowadays, numerical methods have taken over. There are a lot of equations which cannot be, in general, be solved. In fact, the majority of the equations that you encounter in your research or in the practice cannot be solved directly by the methods that we are talking about now. That's a very good comment that I would like to make. Not only differential equations, many equations of mathematics, many problems of mathematics have in principle no solution. For example, you know, e power minus x square dx is a good example where you cannot integrate easily. So such equations, but there are a lot of techniques called these numerical methods which people have invented, and they can solve these problems. That we will not address right now. The numerical methods are very important. We need to have you need to take a good course on numerical methods if your research involves very more intense analysis, design, and so on and so forth. Okay. Once in a while, I would like to make such comments of opinions of my own, but of course you can take them, think for yourself, and form your own opinions about mathematics, their methods of solutions, how we understand, how we learn. All this will become important. Okay, let us look at the first order equations. When I say first order equation, it has got derivatives of the first order only. Okay, it has y dash or dy by dx. X I'm taking as the independent variable, y I'm taking as the dependent variable, y dash, etc. are all derivatives. So this is the form which you can put. F of x. I mean, the general f is any general functional form, not differential form, which suppose like any other functions of several variables x, y, z. Suppose you have a function of x, y, z, the functional form, then you can say f of x, y, y dash is the general form of a first order equation. Only first degree is available. Sometimes you can solve for the derivative. Y dash equals f of x comma y is another equivalent general form. Sometimes you have y dash involved in some intricate way. For example, sine y dash equal to something. Then you may not be able to solve easily into this form, but this is also a good form which can be addressed. And you can easily, in fact, one of the important ways that people do, particularly in differential equations, is you want to interpret this equation either in terms of geometrical terms, in terms of dynamical terms, and so on. So you can easily interpret this equation y dash equal to f of x comma y in terms of the slopes of equations, slopes of curves, and so on. Geometrical interpretation will be very nice in this form. Okay. So what do you mean by the solution? Is an important question here. A solution means we should find out what is this y. Suppose y is a h of x, is some function, whatever it is, and you substitute this into the differential equation. The right hand side and left hand sides match. So this satisfies, h of x satisfies this equation. Then you call it h of x as the solution. Any solution for that matter can, I mean, whichever it satisfies. And many times you are interested only in not the whole range, but only certain range, x ranging from a to b. Okay. Sometimes you are interested in the whole x-axis or so. So here I'm showing you only functions of one variables. We said that functions of more than one variables will be called PDEs, and of course important. We have to learn them, but we may not be able to learn in a small. You see, it's a very nice thing that our ECE-SIAM chapter organizers have done to enthuse people. It's a very good way, actually, in a sort of deviation from your coursework and so on. Of course, this is useful for some people in the coursework also. It is very interesting and very useful to listen to lectures from experts, from your own students, and some tutorial type of classes and some preparatory things for your whatever exams and so on. It's a very good way to do some cooperative work like this. If you are studying yourself independently, you may get lost. It is very difficult to, I mean, you may be requiring a lot of time, and sometimes you may be lost also. It's a very good way to interact with your friends and others to learn things. Okay, that's where the SIAM or the IEEE will be very helpful. Okay, so let us go ahead. So one of the important things that you have to do when you are trying to find a solution, like, of course, once you find a solution, to check whether it satisfies the differential equation is you have to differentiate this, because y dash is there in this. H of x has to be differentiated and then put there. Okay, and you know there are a lot of theorems and a lot of intricate issues when you want to differentiate functions. We should be able to differentiate this also. We should find a solution which is agreeable. Let me use the word agreeable rather than mathematical terms. So that's what is meant by the solution of a differential equation. So you can represent solutions. What do you do when you find a solution? You want to see how it looks. What is the picture of that? Geometrical picture is a very good picture to visualize the solutions of differential equations. So we said the solution of a differential equation is a function, whereas the solution of an algebraic equation is a number, or sometimes only a symbol, not a function. That is one of the main differences between the solution of a differential equation and an algebraic equation. So you can visualize the function. You see the function y is a function of x. So you can plot this. Here an example is given here. See, y dash equals cos x. Y dash equal to cos x. You know what is the solution? Sin x plus some arbitrary constant. So it is a family of curves. As you know, when you see, this is also called, finding the solution is also called integration. This is because if you have y dash equal to some function, y is given by the integral of that function. Okay, whether you can integrate or not is a different problem. So in this particular case, y dash equal to cos x is there. The integral of cos x is sin x. And you know that there are arbitrary constants that come into picture. Any function sin x plus c, when you differentiate and put it into this, will satisfy. So the derivative of constant is 0, so it will satisfy. But when you look at the final solution, y equal to sin x plus c, this arbitrary constant is there. What constant will you put there is an important question. Any constant, derivative will be 0. So c can be anything. And so, of course, for the time being, I will say only real numbers. Later on, we'll use some complex numbers also. There can be differential equations with complex variables. X can be a complex variable, and solution can be complex variable, and C can be a complex number, and all those things. So this represents a family of curves. So you can easily visualize. That's a very interesting feature. Of course, this equation is a very simple one, so you are able to solve and visualize easily. So you can think of, in particular, with first order equations. As you know, the interpretation of derivative is in terms of the velocity in the dynamical systems, in terms of slope in the geometrical systems. So you can think of all those things. Okay, let us get going. So there is one note about modeling in the book. So you would like to formulate your problem in terms of mathematical functions, variables, and equations. Is it not? We want to estimate or measure or calculate. It is not only a design or a model doesn't imply only some specific design or a specific case. We would like our physical system to represent a very broad category of systems. For example, when I say sin x plus c, it can represent any variable, or y equal to a sin x. For example, when I say if a is arbitrary constant, it can represent an array of curves for different amplitudes and so on and so forth. So it's a very interesting part of setting up this model. From the given physical scenario, we would like to set up a mathematical equations for this your problem. So this particular process is called the mathematical modeling. So you will end up in several equations, including differential equations and so on and so forth. So whether you can find the solution and all those things, you can you see, when you represent mathematically, when you address the problem mathematically, we can analyze it and we can get a lot of insight into this problem. There are a lot of examples are there. So radioactive decay is one of the examples usually given. And suppose you have the decay represented by an exponential. See, the solution is coming out to be exponential. Suppose the rate of decay is dependent on the quantity at the starting point, at any given point, not only starting point. So dy by dt is proportional to y. Then you can say that this is exponential, because in many times we work backwards. Suppose if the solution is a exponential function, e power kt, then what is the derivative? You know that its derivative will be e power kt again with some constants in it. So you can say that an exponential variation or decay or rise is given by a first order equation of this form. This is a very good example of a mathematical model. You model the radioactive decay by a differential equation like this, whose solution is like this, and you find that it shows an exponential decay. Very interesting thing. Suppose we don't know that this is dy by dt is proportional to y, then it is not exponential, something else. Suppose I say dy by dt is ky square, then it is something else, phenomena. Okay, so a lot of things are unknown. At the starting of the model or at the beginning of the problem, you don't know many things that we want to gradually look at every aspects. What does k represent? What does c represent? What is the range of values that t can take? And all those things are points of this model. Okay, let us get going. We are not so much interested in this talk. We are not so much interested in the modeling part, but examples are very, very necessary for discussing. Okay, so you know that derivatives are involved. So you can, how do you, when you get a solution, you have seen that there is a general solution. That means any arbitrary constants can be there. But you would like to have one specific solution which meets certain conditions. For example, you want a solution which passes through the origin. So we have to eliminate those arbitrariness or arbitrary coefficients so that it satisfies the given condition. So these are all called various conditions. Sometimes you have the what can be called as boundary conditions. Sometimes you have the initial conditions, particularly when one of the variables is time. Suppose you are doing with a instead of x, you have a time. Then you are given the problem at a particular point. The velocities or displacement or some whatever functions are given at a particular point. Then you have what are called the initial value problems. At x equal to x0, you are given the value of the function. And then the general solution. See, by the way, I must tell you once again that the solution which contains all these arbitrary constants is called a general solution, because any specific solution should be derived from that. Okay, any specific solution should be derivable from that general solution. Then it is called a general solution. And solution which satisfies these particular conditions or initial conditions can be called as a initial in a particular solution. General solution and particular solution, these are the terms that are used. Okay, So I have already mentioned that if you have a y dash equals to f of x comma y, it represents a direction field at every point of the plane. As you know, xy is a xy plane. You can represent points in the xy plane, and y dash will represent the slope at every point. Okay, slope at every point is given by this differential equation. So what is that you are interested? You want to see what is the solution and what happens, how it behaves, and so on. So this is called a direction field. Okay, let us get going. So there are a lot of curves that you can discuss, and also you can get geometrical or graphical solutions by looking at the graph of the differential equation. You can find a solution sometimes. I mean, you can not exactly find, you can understand, or you can guess, or sometimes, of course, you can also measure. May not be exactly, because in mathematics, as you know, you can go for as much degree of accuracy as possible. By looking at the graph of this both the differential equation, you can come to some conclusion about the solutions. So in the previous one, for example, y dash equal to f of x comma y is given. You plot at every point fields of constant slope. For example, you take the value of f of x comma y equal to constant. dy y dash is a constant. So the slope is constant, whatever is the value of x comma y. So this can be called as an isoplane. So by arguing back, you can come back to what is the type of slope. So you can see, I mean, of course, it is shown by small tick marks on this. So tick marks are all constant in this particular graph. So these are all points. You are connecting all the points of constant slope. Okay. So let us get to some methods of solution. So we have just now discussed about what is meant by a solution. What are the initial conditions or the boundary conditions also I should discuss sometimes. You may be given particularly, of course, boundary conditions means there are more than one point. So at point x equal to a and x equal to b, you are given the value to be satisfied, and you find a solution which meets that. Later on, when you go to the second order equations, you will see that you need to specify two conditions. You can specify two conditions at different points in the x-axis. Then you can call them as boundary conditions. Best example is a problem of the vibrating string. You are given that the string has to be fixed at both the ends. So it is the value of the amplitude is 0 at both of these points, and you are required to find a solution. So in that case, you will require the boundary conditions. Then, of course, I would like to extend this when you're talking about PDEs, where you have more than one variable x, y, etc. Then you can specify the condition in a arc. For example, around the circle, for example, like a tabla. So the boundary is fixed. So that is more appropriate boundary conditions you call. Okay. So let us look at some methods of solutions. So how do you solve is an important question. So you are given an equation y dash equals f of x by g of y. See, there are a lot of interesting points that you always need to debate in the mathematics. You always have to see whether the function is defined, whether it is differentiable, whether it has got any points of trouble. Some of you must have heard about the singularities. All these are very interesting points and have to be taken care. But we're trying to understand at first level. Then we'll go to finer details. That is the way to, I think, to get along. So if you have an equation of the form gy y dash equals f of x. So all the x variables I have put to one side, and all the y variables to one side, and dy by dx I have put here. In fact, I can also put, instead of dy by dx, I can put dy here and dx on the x side. So all the x related things on one side, and on the y related things on the other side. So because the derivatives are formed by differentiating the functions, you can expect the solution can be found by integrating these functions somehow. Okay. So sometimes these are all called find the integral. The word solution, but the word integrate is also used for finding the solutions. Integrate these differential equations, we can say. Okay. So in this example, this also is slightly generic form, only slightly generic form, not so generic as we talked earlier. Earlier we said a function of x comma y, etc. So I have separate, if you can separate out y components and x components onto different sides, you can integrate like this. Both sides you just integrate and add this arbitrary constant. Okay. So examples are there. A lot of examples are there in the book. You can get them. So here y dash equals 1 plus y square is what is given. So you can find it, find out. You see, of course, the notation, and of course, I may not have, I just cut and paste sometimes, so they may not represent very well. So you can get different sorts of solutions. You can find out actually for what are the equations corresponding to these solutions. That is an inverse operation. In integration and differentiation, you always do that. Okay. So let us extend this method that we have talked about by integration. Okay. So I have a function of y by x. Suppose the derivative on the side, left hand side, f of y by x. If I can make it in this form, I'm not saying all equations can be put in this form. Some of them, if they are put in this form, there's a trick. So in mathematics, you have a lot of tricks and sometimes a lot of intuition. In fact, the smartness or cleverness of mathematics or the person who is doing mathematics sometimes depends on these tricks. But of course, we cannot depend on the tricks always, but they're very interesting and useful. So if you have a function y by x, then what you can do is you substitute y by x by some other variable u. Okay. If y by x equal to u, then dy by dx equal to, you can put it in this form, u dash x plus u. Okay. You see, the idea is you are having only a function of u, and on the left hand side, u dash x plus u. Okay. So equate them. Now, if you separate out u terms on one side and x terms on the other side, you have very nicely du by f of u minus u by dx by x. Now you can integrate both sides. That's a trick for the, sometimes these are called homogeneous equations, which we would like to reserve. The term is reserved, but sometimes these are called homogeneous differential equations. So terminology, you should be very careful. So there are a lot of examples are there in the book. We need not spend much time on that. Otherwise, we will not be able to cover some interesting areas. So 2xy y dash minus x square. I'll highlight the important points wherever in each of these slides. So you can easily solve that by the technique. So you can easily see that y square minus x square is there on the one side and 2xy is there on the other side. If you match the dimensions, you have the second degree on this numerator and second degree. If you put xy on the denominator also, you can expect that you can put it in the form of y by x and you can solve it. Okay. So, and of course, there's a solution that is given that it comes for this particular example. We're not too much worried about many examples unless it is necessary. Okay. Now, next category of solutions or tricks is exact differential equations. So an exact differential equation can be thought about from the solution point of view. Suppose I have a function u of x comma y and form a differential equation by differentiating with respect to x, with respect to y, etc. Suppose in the simplest way, du is some constant. Du is x comma y. Du is some constant. If I say, then you can differentiate u with respect to partially with respect to x, partially with respect to y, and you can say du is du by dx into dx plus du by dy into dy. Okay. So this is the setting. It may not be possible always, but if it is possible, then the differential equations that have been formed like this are called the exact differential equations. And you can try to find out what is this u of x comma y. We are trying to work backwards. If the solution is of the form u of x comma y, what could be the differential equation and how to solve it? Okay, this is the trick here. And sometimes there can be variations of this by some multiplication factors. Okay, so here you can observe that this has been put in the form of m of x comma y into dx plus n of x comma y into dy. So this can be said to be slightly more generic form of the exact differential equation. And you can try to find du equal to constant or du equal to 0. So if du equal to 0, if is the differential equation. You see, I'm putting in a very simple way, du equal to 0, then you can find u equal to c is a constant. So we have to go back from this equation, mx comma dx plus nx and find out what is this u. That is the idea here. So you can go in a systematic way. In the book, you can see that it goes in a systematic way. So you can say du by dx is m in this, du by dy is n. Once again, you differentiate twice. Dm with respect to, you see here it is with respect to x, so differentiate with respect to y. This you differentiate with respect to x, and d square u by dy dx and dx dy. You must debate here whether both of these are equal or not. Order of differentiation, is it commutative? In algebra, you have seen in the morning, there are a lot of commutations, vector spaces, the matrices, etc. You know, there are commutations. Later on, we'll look at operators of the differential equations also. So whether they can be equated. Under some condition, you can equate under some conditions on u, and you can equate them. Okay. Then you have dm by dy equals dou m by dx. Okay. We are trying to construct back. Okay. So then if you want to find out the original function, you have to integrate m with respect to x and add a constant. Now, because this is only a function of x, you can add a constant. This can be this constant is not really a constant, but a function of y. And then you substitute back and integrate with respect to y. So you will get that u, the function u. Okay, let me take some form. Okay, this is a generic method. This is the idea, basic idea. If you have, let me go back to this form, mx comma y dx plus nx comma y dy. If you have, then you can try to find out a solution by differentiating m with respect to y and n with respect to x. Once again, equating and then finding out what are m and n. Okay. Next. Reducing. See, if it may not be possible to express in the form of u of x comma y. So if you have been, instead of m and n, I have defined that they can become exact. If there are some arbitrary p and q, x comma y and x comma, both are functions of x comma y, you can put in the form of the exact form, like what we defined in the previous slide. So how do you put this in the exact form is a question. The trick is multiply with some function f. I don't know what that function is still, but this f into p and f into q will satisfy the previous d square m by dx dy dou square n by dou x dou y form. Then, of course, p and q are given to us, so you try to find out what is this f. So you reduce this to exact form by multiplying by this function f called the integrating factor. So the interesting part in this is to find out the integrating factor. So how to find it is an important question. Now we can work back like what we did in the beginning. We can work back fp into dx, fq dy, and differentiate with respect to y, differentiate with respect to x, and then equate. And you can find out a solution for f. So that is called the integrating factor. A lot of theorems are there in the book. Specific cases also are there. You need not worry right now in this talk because we'll run out of time soon. Now, those are all the tricks that we are trying to find out. Exact differential equations is one set of course, nowadays people are not so much worried about various forms of the solutions, various tricks directly put in the, in fact, some of these tools like MATLAB, Mathematica, etc., they will give you a lot of cases are already programmed into that. You need not learn specifically. Simply you put the dsolve or some such function and you put your function in that, it gives the closed form expressions also. I hope some of you are familiar. I know I have known about Mathematica, which gives you closed form solutions like what you do. Let us go to linear ODEs. What do you mean by linear ODE? Earlier we said f of x, y, y dash. any function of the form f of x, y, y dash is a linear differential equation, is an ordinary differential equation. So linear differential equation means you have y and y dash separately, not as a product. Okay, that is an operational definition. It's not a real definition of linearity. You have studied the definition of linearity in linear algebra, is it not? So you have vectors which are linearly dependent, linearly independent, and all that. So here, what are the functions that you are dealing with? Y dash, y, and the some function of x. These three are linearly independent. So y dash and y are linear, they are not multiplied. Y dash if you multiply, or y square, or y dash square, or and so on. If sine of y is there, then it is not linear. So there is the other reason why we call them as a linear. Linear differential equations will have a solutions which are linear. Of course, the first order differential equation, you have one solution with one arbitrary constant. Later on, when you look at second order, third order, etc., you have many solutions. So all these solutions could be added. They can be superposed. Superposition is an important and interesting phenomenon. In fact, the idea of linearity also has come from the superposition. You can add two functions with arbitrary coefficients and you say that they are linear. Or the other way, if the functions are linearly independent, you can superpose them. Okay, that is the idea. So an equation of this form is called the linear differential equation. And you have some more, this is called in the dynamical sense is called a forcing function. In the control systems and many other places, you have a right hand side. It's a forced oscillations and forcing function. So if you have right hand side equal to all the linearity is defined with respect to without forcing function. So the set of these equations, linear equations which have got no forcing function or the right hand side 0 are called the homogeneous differential equations. Homogeneous differential equations. If you have right hand side also, it is called the non-homogeneous. This is important from the solution point of view also, not only from phenomenology point of view, but from the solution point of view. So a lot of examples are there, a lot of tricks, a few more coming. So you have first order ODE is an initial value problem, y dash plus y tan x equal to sine 2x. The coefficient is only tan x. This is only sine 2x forcing function, and you can find out a solution. Okay, linear. So in fact, some of these linears will fall within the exact equations and all those things. We'll worry about them as we go along. And there are some equations which have got some variables. See that y to the power of some alpha is there here on the right hand side. This is a very special equation and comes in some important areas. It is called a Bernoulli equation. You forget about the name. So if you have y power n or y power a, it can be any real number actually. Let me say for the example y power n. How do you find the solution? It's a very simple thing. Just as a tricky thing, you simply put u as, see, what I will do is I will divide here y to the, see, y power n minus 1, or if I put this side y power 1 minus n will be there. So see, I'm trying to eliminate on the right hand side. Right hand side I don't want to have the y, so I have pushed it here, but of course it will come below this also. But observe what happens when you have y power 1 minus alpha. So I'll replace it by u. Then there will be a trouble whether it is there in this side or not. So if you differentiate this u, then you will notice that the entire y power alpha or y power n goes off, and this reduces to a linear differential equation. A Bernoulli's equation can be reduced to a linear differential equation. Of course, a little bit of variation is there in the coefficients, but they're all constants. They're not variables. So u dash plus some variable into u plus some variable depending only on x is there. So it is a linear differential equation. You can use the techniques of linear differential equations to solve. I'll now show you techniques to solve. It has got what is it? It has got frozen or okay. I think it has frozen, I suppose, or slides are done. Just let me see. Okay, so you have this sort of equation can be solved by the previous that integrating factor and all that. Okay, so I'll go to one more set of slides. I don't know whether I have some more slides in this. Let me go to. So these are all about the first order equations. First order equations, a lot of tricks can be used even when they are non-uniform, when they are non-linear, etc. But as we go higher and higher order equations, then we'll have more and more trouble in finding out the tricks. Okay. So let me go to second set of equations. But I doubt whether there is any problem with the slides. Let me just see whether something is gone or yes. Okay, I'll go to the second order equations now. I think I should share using the, what is it called? The window. You can ask me one or two questions as we go along, not this one. Open the Chrome and share. Where is that meeting? I'm trying to share the Chrome tab once again. Has it opened or not?
Not yet, sir.
Yeah, just a minute. I'm trying to check what is wrong with that. Let me once again open. Yes, I don't know why Behave has come. I don't know. Anyway. You're able to see the slides now?
Yes, sir. Yes, sir.
So now I'll touch upon some techniques or tricks for second order equations. Okay, so I'm skipping a lot of things in between, a lot of generalizations, then the theorems and definitions, etc. Many of them I'm only going in somewhat a conceptual way. Okay, I hope the technique is all right for the time being. So for those who, of course, the book is very quite systematic, even though a lot of examples are there. It is not a very theoretical book, but at a graduate level in your BTech or so, it is very easy to start with that and then go for more rigorous book like Simon's, or a lot of books are there in differential equations. Now let us look at second order equations. So as I said just now, we don't have so much of flexibility with second order equations. You cannot find too many tricks. Just a minute. Yes. So a general form of a second order differential equation, like what we did for the first order equation, we can put as y. See, we said y dash is f of x comma y is the first order general form, or f of x y y dash. F of x y y dash is the general form of a first order equation. So you add y double dash, second derivative, y f of x y y dash y double dash equals 0 is the general form of a second order differential equation. Okay, now immediately I'll go to the linear form. That was a general form. You can also say that y double dash equals f of x y y dash is the general form of a second order differential equation. So when do you say this? Here the definition of linearity prominently comes out. You see, y double dash is given by p of x y dash, q of x y, and right hand side r of x. So a general form of a linear equation can be thought about when you say that the solutions, if there are solutions, suppose y of y1, let me say y1 is a solution of this equation and y2 is another solution of this equation. Linear superposition is also a solution of this equation. Then we can say that y1 and y2 are linear linearly independent solutions. So one of the theorems in the differential equations is if you have an nth order differential equation, you will have n linearly independent solutions. Okay, that is a theoretical point, but you need not worry. Practically speaking, you will have n equations with some conditions. Always conditions are there in mathematics. So similar to what we did for the first order equations, when the right hand side is equal to 0, you say that it is a homogeneous equation. And as I said earlier, you can specify conditions to reduce these arbitrary constants. Okay, so you can expect that you will integrate it twice. When you want to find out the solution of a second order equation, you will have to do some twice integration sort of thing. That will show you in a minute. So you have what are called the initial conditions. So at x equal to 0, if you are given some conditions like y of 0 is y0 and y dash 0 is y1, etc., then you can say these are the initial conditions and you can solve it. Boundary conditions means, of course, in the case this terminology has come from the dynamics, because there the independent variable is time. So you can say that at the initial point or at the beginning you have these conditions. In the case of space functions, you can have the points at, of course, even in the case of time, you can find solutions which are specific values at the, see, for example, you want to hit the target at a particular point. A missile problem, for example, you're launching from one particular point and you want to hit some other point. So the parameters at the initial and final point are somewhat fixed, given to you. Angle, for example, angle of launching and angle of hitting is given to you. Then you can have a boundary conditions for the initial, that time dependent problems also. For the time being, just imagine that you have 2 points, x equal to a and x equal to b, and you can specify the boundary conditions. So we just now talked about the superposition idea. So if you have two solutions, y1 and y2, as a solution of a second order, for the time being, let us reduce to second order equation. Then you can form the general solution using y equals y1x into some constant and y2x into another constant. C1 y1 plus C2 y2 is a general solution of this second order equation. It is not directly apparent, but intuitive. Then there is also, this is also a theorem sort of thing, or an idea. Let me put it as an idea. If you know one solution, y1x, if you know, you can reduce the order of the differential equation. You can reduce this differential equation to the first order if you know one solution. Okay. There's also a method where you can solve this if you know one solution. I may point out later on. So now get back to some more simplification. Differential equations with constant coefficients. So this is slightly generic form. I have put the coefficient of y double dash is 1 because you can always divide, and assuming all that conditions like dividing by 0 is not allowed and so on, you have two arbitrary constants here. Constants. This is called a constant coefficient differential equation. And of course, you can have a right hand side like what we said earlier. In the beginning, we said that we can have a general solution and a particular solution. So such equations are solved by using what is called the solution of the left hand side for the homogeneous equation with r equal to 0 is called a general solution. And some solution including r of x is called the particular solution. So the total solution can be called as a general solution for a plus particular solution, or sometimes particular integral also. Okay, so let us look at how do we solve the second order differential equation with constant coefficients. The idea is quite simple. From the first order differential equation, dy by dx equal to some constant, we have seen some radioactive decay or something like that. If you have such an equation, you can expect it to be formed by exponential solutions. Y equal to e power x can be considered as a solution to one first order equation if there's only constant coefficient. If there's variable coefficient, you have trouble. So you can expect solutions of the form y equal to e power x. You can find out another solution of y equal to e power lambda to x or lambda dash x. So how do you find out these lambdas? The problem has reduced to finding out these lambda. So you substitute y equal to e power x in this constant coefficient homogeneous differential equation and reduce. You get lambda square plus a lambda plus b equal to 0. This is called the characteristic equation, and you have two solutions. Quadratic equation will have two solutions, y1 and y2. For solution lambda 1 and lambda 2. Okay. Then you can say a into e power lambda 1x and b into e power lambda 2x is the solution. Simple. But you know there is a lot of trouble with this quadratic equation itself. You have identical solutions. Suppose lambda 1 equal to lambda 2. Then these two are not independent solutions. You can get first expression from the second expression by multiplying. So these two are not independent solutions. So that is not acceptable. You must need one more independent solution. How do you get that is the question. So what do we do? Like what I said earlier, if you know one solution, you can get the other solution. So what do? You substitute, say some, see, we have to, this is called a variation of parameters. I think I have put it later on in the slide. So you put some constant a here and consider it as a variable. A of x, e power lambda x, substitute and find out what is a to get the another independent solution. So all these things are done in the book. I have only summarized here. Okay. So characteristic equation. These are the roots of the characteristic equation. These are the types of solutions that you can expect, and this is general form of the solution. If they are distinct, then C1 e power lambda 1x and C2 e power lambda 2x. If there's a double root, you have to work back using the technique which I described, and x is a variable term. So C1 into first part, C2 into second part is the solution. C1 plus C2x into e power minus alpha x. Okay. This is a very interesting thing you should work out. And as you know, when there are two complex roots, that the quadratic equation can have complex roots depending on the value of the discriminant, and they are in conjugate pairs. One is plus and one is minus, and omega is the discriminant. You can say that e power minus alpha x cos omega x, e power minus alpha x sin omega x, and a linear combination of this is solution. You know that cos and sin are linearly independent. So that is about the general solutions. Right hand side r of x equal to 0. Now let us look at some particular solutions. So as I told in the beginning, general solution is the sum of the homogeneous solution and the particular integral. Any particular integral, because you have the generic solution here. So how do you find that? Very simple tricks. You try out, depending on the right hand side, you try out different functions. Right hand side is e power x. You try out e power x, you substitute in the differential equation and see whether it satisfies. And of course, you don't put simply e power x, but generalize. K into e power gamma x is what is tried, and you can expect the frequency not to change. It's not like linear systems. We are talking about linear systems, so the frequency doesn't change. Gamma is remaining same, decay factor or frequency. So the outside, the amplitude part will change. If you substitute k into e power gamma x, you can try. If the right hand side has k into e power gamma x, you try out c into e power gamma x. It definitely, you can easily find out that it satisfies, and find out what is the c for different values of gamma and all those things. Now, if the right hand side is a polynomial, specific case of polynomial is x power n. If the right hand side is x power n, what do you try? N is an integer in this case. So you try out a polynomial, general polynomial of x power n minus 1, x power n minus 2, etc. And all arbitrarily constants, k0, k1, etc. So whenever necessary, you can kill as many coefficients as you want. You right hand side, you take the sufficient general solution, maybe x power n, and then you can find the particular solution. So if there is a cos or sine, what do? You try a linear combination of cos and sine, whether it is cos or sine, both. Sometimes if there is cos, it can become sine also, the solution, depending on the nature of the derivatives, etc. So if there is a cos or sine, you try k cos omega x plus m sine omega x. Then if there is a combination of exponential and cos, you try combination of exponential and cos. So this is how you can find out particular integrals. And this table is found to work perfectly. These all are tried already by everyone, almost. Whoever learns will try this and form this table. Now, how do you find a particular integral in general? For some arbitrary function. is the question. So there's a very interesting problem. We have to find out particular integral. That is the real solving. General solution, of course, for linear systems. And of course, all we are talking about still linear differential equations. So you define an operator. D is the operator, differential operator, representing the derivative. So dy is defined as d by dx. So it is notationally, it is written d adjacent to y. Okay, of course, and the entire differential equation can be put in the form of P of D. This is a differential operator. L is the full differential equation operator, you can say. Say in here it is expanded, d square plus AD plus BI. I is an identity operator. Like you have in the morning you have seen vector spaces. You can also consider differential operators as a vector space, and all the properties like commutativity, additivity, then your closureness, linearity, all those properties can be studied for the differential or this differential operator space. Okay, in this case only linear differential equation is what is considered here, and in principle this is applicable to that, but some extensions can be thought about, like what we did in the beginning for a variable equation, differential equation. So this is a linear differential operator. PD is a linear differential operator. That means if you have two solutions y1 and y2, they can be operated separately by this differential operator, and then they can be added and form the solution and all that. So if this Ly is Ly equal to f of x is the differential equation. Okay, and you will write the solution notationally in terms of operator as L inverse of f of x. So the trick of the problem, or the interesting point here, is what is this inverse of this operator? What is meant by inverse of D? Isn't that interesting question? So if you look at this expression, y, if you have a solution y for y of this small, let us say small differential equation, dy by dx equal to something and y equal to something. So you can say that 1 by d, y is 1 by d of f of x, dy by dx equal to f of x, and y is 1 by d of f of x. Now you know what it is. So L inverse 1 by d or d inverse will represent integration operator. Okay, only d. If you have a P of d, that's a linear combination of all these differential operators, then you can say that there's a more complicated integration operator, L inverse. That can be worked out, okay, by some tricks that we have been trying to do. You can find out what is the L inverse for many cases. For example, what is the L inverse for d square? What is the L inverse for something, and so on. Okay, maybe only linear. I'm trying for the time being only constant coefficients. I'm not saying you cannot do, but it can be done, but not always. Some specific cases, some interesting cases where A and B can be variables also, and you can define a P of D with variable coefficients, and you can work out also. It is there in the book if you would like to see. Here I'm giving the example. Dy by dx equal to e power x is the differential equation, and y equal to d inverse of e of x integral is this thing. So the hint for, in general, finding out the particular integration of any differential equation using the operator notation is to try it for the first order. Suppose you want to find out dy by dx for some x power n into e power x. Then you try it second order, d square, etc. if they are there. Then you try it for the first order and check whether there is some, some clue. Okay, so that is a hint. So now another technique called variation of parameters. Variation of parameters. So the solution is, see, in general, I have put it for px and qx also, not only constants. Okay, these are variable coefficients. And we are trying to find out the particular integral, not the general solution. It is possible to find out the general solution for various these variable coefficient differential equations also. We'll see in a minute. But I'm trying to find out the particular integral for a generic equation with variable coefficients also. So the solution is C1 y1 C2 y2 is the general solution when P and Q are constants. When P and Q are constants, you have C1 C2 constants. Now the proposal in the variation of parameters is assume C1 and C2 to be variables, and then substitute and find out whether it satisfies. So it is possible now by this, what is called this variation of parameters, C1 and C2 being variable, you substitute back and find out, and after some time, you will get a particular integral in this form. See, you already know the y1 and y2 as general solution of the homogeneous equation. And you can find out from the homogeneous equation, you can find out the particular integral. Okay. And this W is the like a sort of determinant what you have found in other domains. W is called the Wronskian and contains y1 and y2 only. And of course, as they are variables, so y1, y2 dash minus y2, y1 dash. So all this can be generalized to nth order differential equations also, not only second order. And of course, all these conditions will be there when W becomes 0, what happens, and all those things. Okay, I'll just give a couple of examples. One example, I'm not solving. This is what is called a Euler-Cauchy equation, where you have these coefficients. Y dash has got a coefficient of x, y double dash has got a coefficient of x square, etc. So by some trick and trial and error, you will easily find, instead of exponential solutions, you can try polynomial solutions. Y equal to x power m. You can try and substitute in this, and you can reduce this to constant coefficients equation and solve. Again, all the determinant, all the 4 cases, equal roots, unequal roots, complex roots, and so on. Only thing is, the final solution will be in the form of C1 into x power m plus C2 into x power m. M1 and M2, not M only. Is it not? There will be 2 solutions, M1, M2, and a linear combination of that. If they are equal roots, what happens? All those things you can think of. So now I would like to jump because we are getting closer to the time. So we'll try to, one generic solution I would like to describe, which is very, very useful, and it gives a very good, interesting. In fact, you can technique, if you run out or come across some equation in your research or somewhere, you can always try this and develop a new technique. It can also be converted into a new numerical method and so on and so forth. Many times, many people invent new techniques for their research problems by such series solutions, numerical solutions, variation of these, and so on and so forth. But at this moment, let us look at how do we solve these differential equations using a power series or series methods, let us call it. So in general, for a constant coefficient differential equations, you may not need this technique, but still it works. For testing purposes, you can try it out on constant coefficient equation also. But in general, it is applicable to variable coefficients. I'm now talking about differential equation with variable coefficient. Second order, third, nth order also it is all right. But let us focus on the second order differential equations. First order also it is okay. But many people, you don't need to worry so much for the power series. Okay. So power series is a polynomial in this form. A0, A1x, A2x square, A3x cube, and so on. A power x, an x power n, plus sometimes it can go up to infinity, sometimes it can be finite also. So a lot of good mathematics is there on the series, algebraic series, power series. And also, of course, you know that there are a lot of other series, not only power series like trigonometric series, then exponential series, Taylor series, and so on and so forth. So for the time being, I'm considering the power series solution of the differential equation. So the idea in the power series is, first of all, you expand the coefficients. Ax, bx, etc. are there inside the differential equation. Sometimes they are already given in the power series form, like x square or polynomials, x square, x cube, or x or something, 1 minus x, and so on. So you don't need to do much about expanding the coefficients. But if you have some trigonometric function or exponential function in the coefficients, you can expand that also in the power series. Okay, then leave them aside. The solution is considered as a power series. For a constant coefficient or a variable coefficient, you can expand the entire function y as a power series like this and substitute into the original differential equation, which means you have to differentiate this and substitute there. And then collect all the terms of x at one point, all the terms of x square at one point, x cube terms at one point, and equate each of them to 0 and find out what are these a0, a1, a2, etc. So the crux of the problem reduces to finding out all these power series coefficients from the differential equation. Whether you can find whether the series converges and all is a interesting problem in the mathematics. So there are a lot of equations which you encounter in the real world also. For example, I'm showing you two equations. This is a Legender's differential equation. The second one is a Bessel's differential equation, and so on. Here you have only polynomials. 1 minus x square is a polynomial. You need not separately expand. 2x is there. N into n minus n is a parameter. Order of the, in fact, you later on, we have not done in this lecture, but these turn out to be polynomials once again. Legenders are finite polynomials, and n are integers. It's also possible to think of special functions. Many times you come out with what are called these special functions. The solutions are considered as a special functions, and you can plot them and see how they behave and so on. Bessel's equations and so on and so forth. Here also you have x square y double dash, xy dash, and some x square minus mu square into y. Some of you may have come across also. So a generalization of this power series method is what I'm trying to describe now as a Frobenius technique. This is a terminology that is used, and you have a differential equation which is put in this form. In fact, you need not worry about putting in this form, but to see, why do we need a generalization of the power series method? Because many times the differential equations will have some odd functions in the coefficients. Just a minute. For the time being, you see, for example, here x square is there, x is there here, and so on. So will you have the solution in the origin? At x equal to 0, y equal to 0, is there a solution? Is there a meaning into that? Whether it is useful is an interesting question. Yes, you need to have a solution at x equal to 0, because if I put x equal to 0 in this equation, there is nothing to solve, is it not? Sometimes, of course, in this particular case, it is not even a differential equation. So suppose there is no x square here, but only x here. So it is important to take care of all those things. So that is the reason this generalization of special series solution has come. And there is for deliberately such a form is taken to both to illustrate as well as to as a generic form. In fact, sometimes this is called a generic form. Even if you don't have x square and x, you can put them. You can divide separately and multiply and then put this in this form. So that is very nicely you can analyze. Okay. So you have as equation y double dash bx by x y dash. So at x equal to 0 also there is a solution we want to find out. And you know that it has to go to infinity sometimes because its denominator is x. So, and also we said earlier, if you find one solution, we can find the other solution by reducing the differential equation. Okay, that is the idea here. So the entire thing boils down to taking a power series which has got a factor x power r. Instead of simply power series starting with x power 0, you are starting with a power series starting with x power r to take care of all these denominator factors. What happens to r is the trouble that you have to find out as we go along. So Frobenius method basically consists of multiplying the power series with the x power r term, and r can be a real number in general, it can be integer also sometimes, and you can proceed further. So substitute, and I'll just describe a few steps, not everything. So you substitute here x power r into the differential equation and simplify it and collect all the terms of x power k or so at one point and so on and so forth. And you finally get what is called an indical equation for r. See, we said r is the troublesome part, is it not? That's what we have to find out. So this is called an indical equation and solve. And you see that this is a second order quadratic equation, is it not? For a second order differential equation, you have r to be quadratic, and you know that quadratic equation, all the trouble of discriminant, real, imaginary, and so on and so forth. So all those special cases will come and find out what it is. So if you solve for a Bessel or one such example, you will get acquainted with all this indical equation and the r factor and all that. Okay. So just describing, I'm not doing much, but there are different cases. Indical equation, roots of the indical equation are distinct. What happens? So there are two solutions. Y1, which has got r power x power r1 and all that series. Y2 is x power r2, all that series. So a linear combination of this is the solution. Okay, that is the simplest case. Then you have the double root. In that case, you need not do anything. You can linearly add, and you can get both the solutions. So when then R1 equal to R2, then you take the first solution as x power R and this polynomial and substitute, and finally you will get something like logarithmic function comes. Earlier, you have seen that in the long ago, in the first set of slides, we have got x into C1 plus x into C2 is what we have got, is it not, when the double root. So you get another solution y1x into ln x into the same thing. Okay, so you can say that this polynomial and including this y1, see this is y1 actually. See, 1 plus log x is what you have got. Okay, log x cannot be derived from these other things. So this is the complete solution, y1 plus y2 in terms of y from y1 you have got. Similarly, there is a specific case if they differ by an integer, r1 minus r2 equal to integer, there is something more special. Okay, so you can do a lot of exercise. Okay, that's what I wanted to put here. So x square into y double dash plus x into bx plus c into y equal to 0. So you differentiate, and everyone for everywhere r power x power r is what is taken as this solution. See, in the beginning I mentioned that these coefficients also will expand, is it not? These two also expanded, and substitute and collect all the terms and find the integral equation and so on and so forth. So this is, if you see, it is assumed that the function is amenable to expansion. B of x can be expanded in a power series, not always. You have to find out what is the conditions on this B. Okay, so you put all the whatever you want to expand in the power series, taking care that y dash has a term of x power r, differentiate and substitute there. That's all is the Frobenius technique. Deliberately, of course, I thought I may run out of time to solve it fully. Then, of course, I wanted to do the Laplace transform techniques, but we have spent enough time on this. I hope that much is enough for now. Okay, I would like to conclude the discussion at this moment. So if you have some discussion, we can do. Yes, please. You are welcome to discuss. I hope I have covered something. Of course, you may be expecting to see this book has got a very interesting part. Every chapter has got a summary, so you can browse through the summaries of this Kreyszig's book. I hope some of you have already used in the college, and you can also form your own. I would suggest for almost everyone, I suppose, because that's the reason why you have attended this talk. Mathematics is important, and in fact, it is a savior for many of our researchers and so on. You can solve your research problems if you are good at some of these techniques. Okay, I hope, but I will repeat what I have said earlier. The interest is the most important part in learning, not just for examination. If you go from an examination point of view, you'll be missing some important understanding part. So please be careful. First you understand, then of course you do the examination point of view, list of formulas, do a lot of problems, and you look at old papers and so on and so forth. So, but I would say the interesting part and some thinking. Okay. Thank you very much for listening. And I hope some of you will join the SIAM chapter and take part in these activities. You can suggest what we can take up. Okay. All right. Any questions, please? Hello.
Yeah, anybody has any questions?
I have a general question, sir. The mention of special equations and special functions. Can you tell me more? What is special about them exactly?
Oh, you see, in mathematics, we start with algebraic equations. When we learn mathematics, we start with algebraic equations. Then you have the trigonometric functions. Then you come across exponential functions. then logarithmic functions. Like that, you keep on accumulating different types of functions and their behavior, their graphs, and so on and so forth. So when the new problem comes, which doesn't fall into this domain of known functions, you take it as a special function. That's how the special functions have evolved. For example, the trigonometric functions themselves are actually a special functions. By this Frobenius technique, if you solve the normal simple harmonic motion type of equation, you get the trigonometric functions as special functions. So there are a lot of special functions like that. So that's how they come out as a special. And some more specific definition, if you want to say, special functions are those which have been got from these series solutions. But it's not a very strict sense definition. But that's what I view them as.
Okay, thank you, sir.
Yes.
Sir, like even if there is any special function, also like can we approximate by a polynomial? So, say example, even if we consider sin x, then it can also be written as in Taylor series form, like
definitely. Both is a finite series as well as infinite series. You can approximate. For example, in general, many of the techniques in mathematics, order of solution or order of approximation you talk about, you truncate up to some whatever degree you want, third degree or fourth degree, then that is an approximate solution. And sometimes, of course, you look at series which are converging, so you can put a limit on whatever amount of computation you want to do. As you know, if there are more and more terms in the series, you have to do more and more computation.
Right.
So people truncate at whatever degree of accuracy they are satisfied with. Of course, you will be losing something sometimes. Sometimes some interesting part may be there after x power k or something.
Okay. Right. Thank you.
Not only functions, the operators also you can approximate. See, that's a very strange thing. Sometimes, see, that is not very apparent, unlike in the case of series, Taylor series or Maclaurin series, etc. Operators also can be approximated. Some of them will have very little effect on your problem or propagation or whatever, wave propagation problems, for example. You can approximate.
Yes.